up on the board here, we have the last result from last time. Let me just say a word about it. So this, I think this is kind of an interesting result. What it says is, if you have some subgroup of a group G, then it's normal if and only if it's the kernel of some homomorphism. Now, we already know that the kernel of any homomorphism is normal. So here to here, we've got covered, right? Well, what if it's normal? Well, last time we showed that this homomorphism that I call pipes of n that takes G, coset Gn, this is playing the role of H right here. And we showed that the kernel of this is precisely n. So that's the other direction. Sounds like a bit of a cheat, but it is important to notice that normal subgroups, they're normal if and only if they're the kernel of some homomorphism. Questions? So when we talk about counting, this is actually one of the most important, interesting things about group theory. It's symmetries and kind of counting arguments, and Lagrange's too. All right, which we'll get to. Let me kind of kick off this. Recall if H is G, then the set of left cosets and by the way, you can replace the word left with right if you like, but I'm going to do this from the point of view of left cosets. Forms a partition. This is a result we've seen, so it breaks it up into these puzzle pieces. The left cosets are the puzzle pieces. The union of all the left cosets is all of G, and two left cosets are either exactly alike or their intersection is infinite, right? Here is something that I've already told you coming back. Let A in T be segment. And X, Y, two left cosets of H. So two random cosets, then they are the same size. Whether they be finite or infinite, they're cardinal. We talked about this earlier. Let me give a quick proof. This way. I'm sorry, there's H. So if they're left cosets, then capital X is this left coset and capital Y is this left coset. Here's the bijection. By the way, let me point out this function I'm going to give you is not a homomorphism. In fact, this thing usually isn't a group. In fact, this coset, this left coset, is a group if and only if somebody give me a condition on X.
It's the idea.
That will work, but there's a broader condition. He is correct. What's it? Oh. So what he said is true. If X is the identity, then this coset is in fact in itself a group. But there's something more general to say the X is the identity. Anybody know what it is?
Well, meaning that H is the same subgroup, basically X is multiplied by H, while the same element says E of H, you know?
Okay, well, let me put that another way. I think you're spiritually correct.
Because they have the same element smaller.
It's an element of H. Right? So, in fact, there's only one coset that's a group, and that is the one that corresponds to EH. But that coset represented could be anything in H.
Mhm. That's what I'm saying, you know? If there's anything that's all multiplied any elements, you know?
So here, I'm going to define a function from the left coset XH to left coset YH, and pitchfork takes. Where should I go? Remember what a simple-minded fellow whose parents are cousins I am. What's the easiest image that I can come up with? There you go. This is a bijection, right? I'll go through this really quick. By the way, I can't use the kernel thing that I really like to do for one-to-one because this is just a function. It is not homomorphism. Suppose that XH equals XH prime. This means that YH equals YH prime. Now multiply on the left by Y inverse, and I get H equal H. Everybody okay? Right. So from the first. And pitchfork is 1 5. How about onto? This was, I think, easier. What goes to it? So what we have a bijection from the elements in here to the elements in here. So this is an important takeaway, and this will help us be especially useful when we're talking about doing things in finite groups. Although it's not useless for infinite groups, it's most strikingly useful for finite groups. But the left cosets are all of the same size. Okay, there. Here is famous theorem of Lagrange. Let G, yeah. Let G be a finite group. And H and G is subgroup. This is kind of, to me, this is like one of the first really big striking theorems about symmetries in group. Then the order of A varies. The order of P and this number is equal to the number of left cosets of H and P. So if you've got a subgroup of a group, then the order of that subgroup has to divide the order of the group. And whatever that quotient is the number of left cosets of that subgroup. So if I walk up to you and I say, hey, look, I've got a group with 100 elements in it, and I found a subgroup of order 30. You can say, haha, no, you didn't. In fact, if you've got a group of order 100, what are the possible subgroups? That was it's 10 squared, isn't it? And A is in G, and order of A, and only about 100. Those are the only possibilities. 1, 2, 4, 5, 10, 20, 25, 50. That's it. No subgroups of order 30, no subgroups of order 8. Yes,
I feel like I remember you talking about this way earlier, like a couple weeks ago.
I mentioned it, I'm sure.
Yeah.
Right. But now I've sort of
Now
made
you
it,
said it,
yeah,
yeah.
now we're Facebook official or whatever.
I just thought it was cool. Great.
This is a really cool theory. Let me also point out this dangerous thing. These are the possibilities. There's no guarantee on the surface of it that you do have subgroups. So, but these are the only suspects. Right? I can think of a group of 100 that has to have a group of every one of those ones. You might think of type of group that will order 100 that for sure will have this kind of stuff. It might help to cycle through your notes. A cyclic group contains a subgroup of order n for every divisor of the order. And not only that, not only does C100 have all of these possibilities, but there's only one for every possibility. So there's a unique one. Now, other groups like this is, yes, sir.
You said a sentence and hate usual suspects, but I think that's the rest of the sentence. Something about like these are the usual suspects. Or
Oh, these are the only suspects. If the group is of order 100,
Okay,
any subgroup has to have one of these orders.
does that mean those are all like you? But what you just said is that doesn't mean those are all.
That's right.
Okay.
I know that
Usual suspects.
if I have a subgroup of a group of order 100, it has to be of one of these sizes. And just because I've got this size, or just if I walk up to you on the street and give you a group of order 100, it may not contain a subgroup of order 10 or 20.
Okay.
And I'll give you a concrete example. For example, so here's and we're actually gonna prove this later. Of course, you can prove this long-handed, but it'll make it cuts because it's a big mess. What's the order of S5? 30 and 40. 5. 1 point. But S5 has no subgroups of either order. As it turns out. Here is kind of, so Henry, here's another kind of preview. We'll come back to this later. It turns out that any group of 400 has to have those subgroups order 2 and 5. S5 has subgroups of order 2, 3, and 5 for sure. We're gonna prove that later. What is special about all these numbers that I have given you here?
They're all prime.
That is correct. If you have a finite group and a prime divides it, then there has to be some battle. And we will prove that way. Okay. Anything. Okay, and look, well, let's do the proof of this. Proof of God. Since left cosets of H and G partition G, then we can write uh, 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 where x1 H, x2 H, x2 H are the distinct left cosets of H and G. Okay. Always good to be critical of old Jim. The first thing that you might say is, Jim, how do you know there's only finitely many in the union? Anybody tell me why?
It's a finite group.
That's exactly right. What do you know about these pieces of a partition? They're all non-empty, right? So there's at least one element in each of these. Everybody agree with that? There's at least one element in each of these sets, which means, and these are disjoint sets. So the biggest n could ever be is the order of G. Everybody agree with that? If G has n elements, well, if G has, let's say, m elements, then the biggest this could be is m. Right? So this has to be a finite union. Right, okay. Since the cosets are disjoint, the number of elements in G is the number of S1 H plus S2 H let me also point out that any one of these cosets that's what we just proved, 421, that all the cosets have the same size. They're all the size of the sub H. So what do we have? In this equation here, all of these things are the same size as the subgroup H. And how many of them are there? There's an n. Immediately we get that the order of G is some integer times the order of H. So H divides the order of H divides the order of G, and the order of G of the order of H is n, which is the number of distinct left cosets. Yes,
There's something about proving this long-handed, what is that, like, this like a, and, you said something about proving something long-handed. Long way, I don't know, maybe I'm.
you never can't tell what's gonna come out of my mouth.
Okay.
I don't really recall what I said.
That's okay, I just.
Anybody help him out? What did I say? Rosie?
Says something like you can prove it's a long way or something long way, I don't know, I was wondering if this is a valid proof, right? This is-
Absolutely.
Okay.
Yeah, absolutely. Yeah. I may have been speaking about something else.
I mean.
So, right, so. Here. Remark. In. We found this earlier, this didn't call it together, or bring it together again, it's also called the index. Of HED. And it's just the number of left cosets. That N is by the same notation from this. So, give you a corollary, like an unnumbered corollary here. Oh, no, so I'll come back to this. Um, 14. Let G be defined. And X your favorite element. Then the order of X divides. Remember what this is, the smallest power of X, that is the identity. Proof. Let N be the order of X. So the subgroup generated by X consists of the identity X, X squared, X to the N minus 1. These are all the powers of X, and when they hit Xn, it cycles back here, and I go through the cycle again, right? So the order of the subgroup generated by X is N. It's the same thing as the order of X. So the order of X divides order of G by the bunch. Remember, this is the big connection in the notation between order of an element, order of a group. The order of an element in a group is the order of the subgroup that it generates. Okay, let me give you an example. And I'll tell you explicitly what the order of this group is. That's my number. Big set. The number of different combinations that I can put on this, or the number of scrambles that I can do on this cube is that large number. That's the size of the group. Let me give you some examples. If I do this, if I call that X, that's X squared, that's X cubed, that's X4, that's X5, that's X6, like where I started. The order of that move was 6. Right? Notice 6 divides this number. Right? What is the smallest integer? Oh, and y'all remember me going through all this when I went like this and kept going over and over again. Remember, it took me a while to solve it, right? That particular element had a order 105. 105 times we get back to solve. That little subgroup generates subgroup order 105. Notice 105 is 3 times 5 times 7. There's a 7 there, and also a 5, and there's a 3. So no problem. Right? What is the smallest positive integer such that there is no move I can do on the Rubik's Cube that will come back, that has that will come back exactly 3 times? What's the smallest unallowable one? Who said 13? 13, that is correct. Everybody agree with that? Because would everybody agree that 13 does not divide this? Because 13 is a prime and it can't divide anything, so it can't divide, right? But everything up to 13, I mean, 1 through 11 divide that, so you got that taken care of. And 12 goes into this, right? 13 is the smallest integer that doesn't divide this. And in fact, on the Rubik's Cube, I can find you some rearrangement of order, anything you want. I just did a 6, but I can find anything from 1 to 12. But 13 is impossible. Obviously. Okay, any questions? Okay, how about this? Using our index notation here. Anybody want to guess what this is? What are the number of left cosets of this inside this? That is correct. You're correct in spirit. Very close. Let me give you an example. Let's do a concrete example. Because I think you can generalize this easier, right? So what am I doing? I'm looking for all the cosets of 5Z, left cosets of 5Z and C.
Doesn't Lagrange stay along and work for finite groups?
Oh, you can still have a finite index. I'm not making a claim, but I'm not saying that the order of the subgroup divides this, because you get 2 infinities.
Right.
All I'm asking you to do is count the number of left cosets.
Are you talking about the left count?
Yeah. There's the group itself, right? All multiples of 5. What's another coset? In fact, just for dramatic purposes, because I'm that kind of fellow, I might write that. Remember, here are operations addition. What's another coset? Okay, 1 plus 5Z, which is basically all this crap with one.
There's 5 of the C cosets.
What's it?
There's apparently 5 in coset. Because you're gonna do like 5 + 5c, then just be it form shifted to a left, which considering an infinite, set which is 5c, will probably just be the exact same thing as 0 + 5c.
Well, what you've done is you shifted everything by one, so there's nothing in common here and here, right?
Yeah, but you should do by 5.
That's correct. When you shift it by five, you come back.
That works in infinite sense for now.
And then, as was pointed out, you cycle back around. Everybody agree? So everything that is an integer is in one and only one of these cosets. Right? 8675309. Which coset is that in? Let's not let Tommy Q come down. What's that?
4 + 5c.
Correct. How did you get that?
It has 9 in it. And I know that anything 5, yeah, and you know what I
Yes. So what he did very quickly was, this is 5c, you divide this by 5 and take the remainder, and that tells you what coset it's in, right? And of course, this junk is already divisible by 5, leaving you only with a 9, right? 9 divided by 5 gives remainder 4, so 8675309 will end up in this one. I agree with you. Okay, so if what? We'll say that n is in the natural numbers, or n in the natural numbers. What happens? See. Because now your H is just 0. Right? And so the left cosets will be, you've got only the 0 subgroup, right? So every element will be its own, every element of Z will be its own coset, right? And so what you have there is it's in. Okay, any questions on this? Okay. Here is another really groovy corollary. What do you got? We've already classified all the groups that are cyclic, right? A cyclic group, a cyclic group is either isomorphic to the integers or it's isomorphic to Z mod n Z, where n is the number of elements in time. Now we're going to classify all groups for prime power. Suppose I give you the following information. I have a group of order P. What can I need to make sure we all know that because this is very dependent on how people. You might know what I can say about the group.
only like subgroups of one of order one in itself.
Well, that's true. G is 60. And in fact, G is isomorphic. Up to isomorphism, there's only one group for P. Let me go through a quick proof of this. Well, any identical thing. Okay, let's go with this. This P is prime, P is greater than or equal to 3. So there exists X. There is an element in there's an element in G that is not the identity. Because you gotta have at least two elements. Right? What's the order of X?
P.
No choice. It has to be P. Because the order of X is not 1 because it's not the identity. Right? And it has to divide the order of the group. What is the only thing that divides a prime? Prime itself. The order of X has to be P. So the subgroup generated by X in G has a form P. So group generated by X is equal to G. Because G is order P and X generates a subgroup of order P, so they have to be equal. So G is cyclic of order P. So G is isomorphic. Fantastic. Just to show you that this is kind of striking. Let me give you an example. If order P square, where P is cyclic, or I'm sorry, P is prime, then there exists at least two different groups. That is, two groups formed squared that are not isomorphic to each other. One of them, by the way, somebody give me one group P squared. There's always a cyclic group. One of these Z mod 4, Z mod 9, like that. You want to give me another example, one that's like this. I'm going to do this example here because it's cyclic, but there is another, but one that's structurally different. Let me show you how to build this, and this might open your eyes a little bit because this construction we're going to generalize later. This shows you a way to take a couple of groups and build a new group. What do I mean by this? I think that the notation is suggested in the sense that you've seen some mathematical construction before you look like this. I'll call this, X1, well, I'll look at X, Y. What's the X, Y, R, B, C. And this is under addition. Right? So the way it's gonna work. This is the most simple-minded thing I can think of how to build a group with sort of a vector notation. Is, remember, this is math, we don't do anything unless it's easy. How do you get the new first coordinate? Just add up the old first coordinates. How do you get the new second coordinate? You add up the old second coordinates, right? Okay, if I say this is the way my operation is, can somebody tell me what the identity of this group is with the pairs?
Serious man.
0, 0. Everybody agree with that? What is the inverse, additive inverse of XY? Negative X, negative Y. And they both exist because each one of these coordinates is a group, right? So you got the inverse from both, right? It's associative. Please don't make me do this. It's associative. I don't want to go through it because both groups are associative. Basically, the two components work separately, right? Everybody okay with that? And let's see, the inverse, identity, associativity, and it's certainly closed because both coordinates are still in Z. Right? How many elements does this have? P choices, P choices. This is word square. Can somebody explain to me why this thing right here is not isomorphic to this? Why is this one not cyclic? Well, this one's cyclic, of course, because this is 0, 1, 2, all the way up P squared minus. Everybody agree with that? And the element 1 is a order P squared, because you got to add it to itself P squared times to get back to 0, right? What are the orders of this element? 0, 0 has order 1. Well, what if one of the entries is non-zero? What's the order? It doesn't matter if one of them is 0, as long as they're not both 0. Everything in this collection here, with the exception of the element 0, 0, has order P. Right? So there is no element of order P squared. Because if you take any xy, if you add it to itself P times, you will get 0, 0. Right? So there's no element of order P squared here, so this can't be cyclic. Now, this probably opens up something a little disturbing for you, perhaps. Now, if I tell you that these are the only two groups of order P squared, and they are, maybe you're not so confident, right? Because how do you know that somewhere deep in the depths of some Stephen King novel, I can't come up with a third group of order P squared? That it turns out I can't, right? That's it. Every group of order P squared looks like either this or this, but that is not clear, is it? Is it clear to anybody? Yeah, but here's something else that's true. Every group of order P is cyclic, abelian. Every group of order P squared is abelian. How many groups of order P cubed are there? There's 5. 3 of them will be abelian, and 2 of them are not. Right? 16. By the time you get let's say, so there's, for example, 5 different groups of order 8. For groups of order 16, I think we're already up to 14 different groups of order 16. Right? So there's lots and lots of things. How do we tell them apart? How do we know when we've got them all? Yes.
You say that there are
only five, you're saying that we know for a fact that there can only exist five numbers that we only know of five.
No. There are only five.
There are
That,
only
there
five,
there are
okay.
only five, right? But there are a lot of actually kind of basic, sounds like day one questions in group theory that you can ask that are not clear. Okay, just,
Are you taking those memorized, or are you doing that in your head, figuring out how many there are?
I've been this a long time. No, I didn't do that on my head.
Okay, I was thinking it was like
I mean,
a trend or
the-
something.
Yeah, the groups of order eight are, Z2, 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 Z4, ZA, so those are the three abelians. And then there's dihedral on the square, and then there's fraternities, and that's it. But it's not clear anymore, is it? Because now that I came up with that example, who knows what other kind of crazy yin yang I can do?
But they'll all be isomorphic.
Right. But if you walk up to me on a street and give me a group of eight, it is isomorphic to one of those five that I just knew. It has. Okay, so here's a big one. This one's a big one right here. And I will not have time to prove this today, so I'll probably sprinkle this kind of a little follow-up here, and we'll go through the proof of this next time. But this one's a big one, and this is the one that I kind of teased you with a little bit earlier. Let G be a finite order. And E, a prime number, such that B divides it. Then there exists X and G such that the order of X. This is a huge theorem, right? So for example, I'll go back to the Rubik's Cube group now. If R is proof on 3x3 Rubik's Cube, that is the proof of scrambles, then the order of R is 11 factorial times 8 factorial times 3, 8 times 2, 12. So distinct primes dividing the order of R are 2, 3, 5, 7, 11. Cauchy's theorem says for each of these, there exists X and R such that the order of X. So there's some scramble. Some of them are easier to find than others. Let me show you a scramble. Two. That's X. Do it again. Yeah, I feel a little cheap every now, right? But these are hard to find, right? One of the things that you can do on a Rubik's Cube, which I won't do here, is you can take this piece to here, this to here, and this to here. So you can sort of cyclically shift these three, but I would have to do a lot of moves to do it, well, at least I would. And if I do that long X 3 times, it'll come back. There is a move of order 11 on there, for sure. I'm not guaranteed any product of these. I have seen an element of order 6. I know there's an element of 12, which is 2 squared times. I know there's an element of 105, which is the product of these. But is there is there one of order 11 squared times 3 cubed times 5 squared times 7? Actually, that one I think no. It's a matter of fact, because the largest order is 1260. Oh yeah. So check this out. The element of largest order in R 1260. I don't expect you to know that. It's just, you can just take that as a fact that you looked up the internet, which never applies. And this is 5. This is 7 times 18, which is 2 squared. No, actually, let's see, there's another one. Yeah, 2 squared times 5, it's 3 squared. It's 5. 7. Notice that the only primes involved are a subset of these. And also notice that this thing divides the order of Rubik's group. Right? So there does exist an element on this. We don't know about 5. I do know there's no move order 13. I do know that. Okay, so any questions? All right, we will tackle Cauchy next time. And we'll see you on Friday.
Yeah, Friday.
So I checked. So they, you use the file, I showed